On behalf of the International Center for Theoretical Sciences of DIFR, ICTS DIFR, let me welcome you to this inaugural lecture of the Technology and Cosmic Frontiers series. We are thrilled to begin it with this double bill today of Kip Thorne and Rana Adhikari, and we'll hear from both of them how cutting-edge science synergizes with technological advance. And one purpose of this lecture series is to sow awareness of this whole process and the synergy between fundamental science and technology, and create that awareness in India and hopefully harvest its fruits in coming years. This is a topic which is, I think, very close to Vijay's heart as well. So let me first ask the distinguished scientist and principal scientific advisor to the government, Professor K. Vijayaraghavan, to briefly share his thoughts.
Thank you very much, Rajesh. It's a great pleasure to be here, and with lots of trepidation. I'm never sure who knows the secret of life, whether it's cosmologists or biologists, but in any case, it's really terrific to see the intellectual heft here at the start of the series, and I'm sure it'll go well. The principal challenge which we have in ventures which strike at the frontiers of our knowledge and broaden our understanding is forever trying to balance that excitement, that sense of adventure, with the very, very proximal demands. And in that, physicists all over the world and astronomers and now cosmologists have managed to do that exceedingly well. Their numbers are small, but their impact has been enormous. This is an amazing achievement because similarly, get such missions launched by thousands of people working together in other areas where very valuable explorations can be done are very, very difficult. And I'll come to one of those a little later. I'll be brief, but I'm very excited about what's happening in LIGO in India. It would be perhaps one of the few major science missions on this scale and on this ambition, and which will link to industry in an enormous manner. And we're already seeing signs of that in terms of getting vacuum in place and so on and so forth. Now, the challenges which we face in discussing LIGO and taking it forward are two. One, the explorations are expensive, and that can be dealt with by arguing that while that's the numerator, the denominator of impact on industry and on people is enormous. However, for many big science missions in physics, that denominator in India is still very small. If you take CERN, for example, the numbers of people in India working on CERN-related projects is modest. It's grown enormously recently, but it's grown linearly. Whereas if you look at some European countries, the numbers of people are very large, and the programs which use data from CERN in university systems is very large. That's what we need to do with LIGO. And in a recent discussion on LIGO at a very high level, this was a factor which was highlighted. And another factor which is actually taking place really well is interaction with industry. So expanding the denominator takes care of the concerns about the expense, and I hope that LIGO-India will be approved very soon. But as you all know, and I should not be saying this to this audience, gravitational physics has got a deep tradition in India. We have Bala here, we had Dhurandhar, and several others, Vishwesharaya. This is really an area where theory and experiment come in beautifully, and Kip and Rana symbolize that link between theory and experiment in an extraordinarily beautiful and elegant manner, where patience in developing technologies, keeping light of technologies as they develop and using them has been extraordinarily valuable. So I won't take any time more. I mean, we're here to listen to Kip and Rana, but I would like to say that this series is facilitated by the Office of the Principal Scientific Advisor, and we will explore many other areas as we go by. And I thank particularly Rana Adhikari for helping put this together, as also our colleagues at the ICTA. Thank you very much.
Thanks very much, Vijay. So on to the program. We have a real treat, as I said before, with Kip and Rana guiding us through the exciting science of gravitational wave astronomy, as well as the new technology it will generate, and the prospects for both of these in LIGO-India. So let me briefly introduce the speakers. So first, let me begin with Rana Adhikari, who is truly one of the stars of current day gravitational wave physics and technology, and professor of physics at Caltech. Rana has been working on gravitational wave detection for 20 years with a focus on precision measurement to discover new phenomena in gravity, quantum mechanics, and ultimately the true nature of space and time. His work has been recognized by the 2019 New Horizons in Physics Prize of the Breakthrough Foundation. Rana has been at Caltech actually almost right after his PhD, going on to the faculty in 2006. And his PhD was at MIT with Rainer Weiss, the co-Nobelist with Kip Thorne for the discovery of gravitational waves. Rana has been a regular visitor at ICTS as our senior faculty associate and sort of a great well-wisher of our institute. He is one of the original proponents of LIGO-India, in which he is heavily invested and has been working tirelessly to build a community of physicists and engineers who sort of build and operate LIGO-India. And we hope this dream will come true. Our first speaker is of course Kip Thorne, the Feynman Professor Emeritus of Theoretical Physics at Caltech. Kip is a living legend in both science, among scientists, as well as in the public imagination. His popular science books, Black Holes and Time Warps, as well as the Science of Interstellar, the latter was based on the movie into which he gave critical scientific input. These have had a wide readership in the general public, but probably less known to the public are his many contributions to the understanding of Einstein's general relativity, and in particular, two of his blockbuster physics books. The first on gravitation with Charles Misner and John Wheeler, and more recently on classical physics with Roger Blanford, also on the advisory board of the ICTS. These are absolute tour de forces of exposition and literally breadth and depth, if you've seen the books on the subject matter. So at ICTS, we especially recall Kip for coming in person for the inaugural Vishweshwara lecture. And this was a very special event in the history. It was actually the 10th anniversary of ICTS, and it was like a rock concert held in our outdoor foyer. We can only sort of fondly reminisce about these big gatherings now in our current state, but it was very special, something really special and memorable. I will not bother to list all the honors that Kip has. You can find them on the internet, except to say that it's, of course, it's a very, very long list, and but crowned by the Nobel Prize in 2017. So, without any further ado, it's. But before I actually hand it over to Kip, let me just say a few words about the protocol. Please type in your question and answers in the chat box, whether you're on Zoom or on YouTube. This will be moderated by Professor Ajit Parmeshwaran from ICTS. At the end of both presentations, there will be a 20-minute question and answer session, and Ajit will take up some of the questions from the chat windows and direct them towards the speaker. Because now let's begin with Kip.
Hey, can you hear me?
Yes.
Let me share my screen. That's strange. Okay. Can you see my screen now?
Yes.
Okay, thank you. So it's a great pleasure and honor to participate in this inaugural lecture. I thank you very much for inviting me. So according to the laws of physics, there are just two types of waves that can be created in the distant universe and travel across the universe, bringing us information about what is over there. Electromagnetic waves, which of course include light, X-rays, radio waves, and so forth, and that consist of electric and magnetic fields of forces that oscillate transverse to the direction that the waves propagate. And gravitational waves. Gravitational waves, as predicted by Einstein, consist of a stretching and squeezing of space. And so if I have an array of particles out in space where there are no other gravitational forces except the incoming gravitational waves, and if the gravitational waves are propagating into your screen, so you see this array of particles, as the waves pass and they stretch and squeeze space, the particles move like that, being stretched with space and squeezed with space, again, perpendicular to the direction of propagation of the waves. And so that was Einstein's prediction about the nature of the waves. And Rana in his lecture will describe how LIGO gravitational wave detectors make use of this stretching and squeezing in order to detect the waves as they pass. Now, it was 400 years ago, approximately, since Galileo built his small optical telescope, pointed at the sky, discovered the 4 moons of Jupiter, and in the process created modern instrument-based electromagnetic astronomy. And since then, there have been enormous changes in our understanding of the universe due to this electromagnetic astronomy, of course. And it is now just 6 years ago that LIGO turned on and saw gravitational waves from 2 colliding black holes in the distant universe and initiated thereby gravitational astronomy. So LIGO has done for astronomy the same thing as Galileo did 400 years ago. LIGO consists of 2 gravitational wave observatories at the present, one in Hanford, Washington in the United States, and the other in Livingston, Louisiana. And we are looking forward enormously to the 3rd LIGO gravitational wave detector in India. I will return to that later in my talk and describe what LIGO-India will bring to our gravitational wave astronomy. Now, the first signal that we saw with LIGO was due to 2 black holes colliding 1.3 billion years ago. And that is so long ago, that is when multicell life had just formed on Earth and was spreading around the world. And this is a computer simulation of what those 2 black holes would have looked like to your eyes if you had been there as they spiraled around each other and collided and merged. What you're seeing is the 2 black holes in front of a field of stars and dust and gas that are behind them. And it's the bending of the light rays by the gravity of the black holes that creates these swirling motions. We call that gravitational lensing. And as those black holes spiraled around and around each other, and then emitting their gravitational waves. They collided, they merged, and they produced an enormous burst of gravitational waves, went traveling out across the universe, bringing us the signal that LIGO detected. That is not real. That movie does not really give you a real sense of what these black holes were and what they were doing. The key thing is that black holes are made from warped space and warped time. And so I'm going to show you that by imagining that the orbital plane of the two black holes is embedded in a higher dimensional universe that enables us to visualize the curvature or the warping in space. And so you see, in fact, two funnels that dip down in this higher dimension, and each of them is a black hole, and the color coding is representing the slowing of time near the black hole. The black holes themselves, the interiors, I will depict as black. This is from a computer simulation by a numerical relativity group called the SXS group that produced much of the simulations that underlie LIGO's gravitational wave observation. And so we're going to watch as these two black holes spiral around each other, and the warping of space and time becomes more and more extreme. I've slowed the movie down, and I'm going to pause the movie right when the black holes collide, when their horizons, their surfaces merge. So the huge splash in the shape of space and time, and then the gravitational waves go propagating out through the universe. And that enormous splash is what produced the great burst of gravitational waves at the end. Now, the shape of space at the moment of collision looked like this, and you see the gravitational wave form, the shapes of the gravitational waves look like that. So what I'm plotting here is upward is the stretching of space, downward the squeezing of space as the gravitational wave goes past. So there's oscillation between stretching. This is along one of the axes, say the horizontal axis. The stretching, squeezing becomes faster and faster, and ultimately comes to the moment of collision. And then right after the collision, the black hole, the final black hole, then begins to ring like a bell, oscillating as it dies, the oscillations die down. In fact, just as if you hit a bell at different locations, you get two slightly different, you can get different tones. You get the fundamental tone of the black bell, and then you can get some harmonic of that fundamental tone. So similarly, when the black holes collide, it turns out were in this collision, there were two normal modes, as we call them, two tones that were excited. We didn't really understand that until just a couple of years ago, several years after the gravitational wave was observed, and it required the people doing the numerical calculation to go in and do extensive numerical calculations, studying the details, and they realized, in fact, quite a rather amazing fact, that the gravitational waves are all coming from outside of this region here that I've dotted around the colliding black holes. And outside of that region, at the moment of collision, the gravitational waves then are outside that region. The space and time geometry is almost that of the quiescent final black hole, except for the disturbances, but modest disturbances. And because the disturbances are modest, in fact, the gravitational waves from that point onward are really due almost entirely to small perturbations, we call it, small disturbances of the final black hole. Sadly, we don't see gravitational waves from the enormous storm, what we call the geometrodynamical storm that is going on inside. That's very unfortunate. On the other hand, as we understand now from these more recent simulations, that the gravitational waves from these two modes of oscillation enable us to do some marvelous science. And this is an example of the science that has been coming from LIGO. From those two modes of oscillation, from their frequency of oscillation, and each one has a frequency, each one has a decay rate, we can infer the mass of the final black hole and the spin of the final black hole with very good accuracy. And we get that signal for the entire ring down period, as I have explained. And using that fact, we can test what is called the black hole uniqueness theorem, which says that the mass and the spin of the black holes themselves, just two numbers, determine all of the black hole's properties. And so if you have two numbers, they determine the frequency and the decay rate of the strongest normal mode. And then you had better get the correct prediction for the observed frequency and decay rate of the other normal mode. And indeed you do. You get the frequency is measured with rather good action. The decay rate is measured with less good accuracy. But when you look at the data from this first observation, you see that in fact, the mass and spin you infer from the first normal modal oscillation also predicts the correct frequency and decay rate of the second normal mode. So this verifies this fundamental property of black holes predicted by general relativity, that all of the properties are determined by just those two numbers. Another thing that can be done now with these normal modes is to test Stephen Hawking's laws of black hole dynamics, marvelous and really powerful laws that he, together with colleagues, predicted back in the golden age of black hole theory, way back in the 1970s. In particular, from the mass and the spin of the final black hole, one can compute the surface area of the black hole, the area of the horizon around the black hole. And then from the inspiral waves, we can compute the surface areas of the initial black holes. And Hawking's theorem says that the surface area of the final black hole must be bigger than the sum of the surface areas of the initial black holes. And the observations of that very first gravitational wave signal tell us that this really, with 97% confidence, that this really is true. And the paper that tells this is from my physicist colleagues, was just published in Physical Review Letters by the Numerical Relativity Group and the LIGO data analysts who did this. A paper by Maximiliano Isti at MIT and colleagues was just published a few weeks ago. By now, since September of 2015, LIGO has observed 67 gravitational wave events in total. Here I'm plotting observation time since that time. And you see it's about 750 days. Of course, there's been a lot more time than that since then. But what was done was about 120 days of observations. Then LIGO was shut down for some months to improve the detectors up, and then it was turned back on. And we got up to 400 days of observations. It was shut down again for improvements. Then it was turned on and run up to 750 days of observations. We call that the 01, the 02, and the 03 runs. The 03 run was just split into two pieces for the purpose of publication and of the data. Public data are pretty fully published up through 03A, and the last part of those data are just beginning to be published. But the important point is here is the cumulative number of events as a function of time. You notice it was a slow process initially because the detectors were not all that near their design sensitivity, and then a huge improvement in the sensitivities at the beginning of the 03 run due to spending many months improving the detectors, and a very steep rise up to the 67 events total that have been seen by now. And toward the end, it was getting up nearly to an event a day, something like maybe 2 events a week toward the end of it. So there's been an enormous amount more learned with these observations in that period of time. And so in particular, here are a few examples. There is a very interesting source, GW190521. That means it came in on May 21st of 2019. This is the most distant and massive black hole that's ever been seen, 7 billion light years from Earth. That is, that's half the distance to the edge of the observable universe. The two black holes, 85 times as heavy as the sun and 66 times as heavy as the sun. The total is 142 times as heavy as the sun. This black hole is, according to theory, our understanding of the theory of stellar evolution, is too massive to have been formed by the collapse of a star. So it almost certainly was formed by the merger of two other black holes to create this black hole. And similarly, this is so large that it was probably formed by a merger of two other black holes to create this black hole. So for the first time, we have observational evidence that you have hierarchical mergers, one after another, in some sort of very dense cluster of black holes that in the distant universe. It had been expected that this might be the case, and this is now confirmed. Another example, and these are just two examples of the rich science that has been done. The most asymmetric binary black hole, BBH is binary black hole, two black holes going around each other. A 23 solar mass black hole and a 2.6 solar mass. Well, is it a black hole? This is actually much lighter than any known black hole for which we've ever had any evidence. And it's too heavy, however, we think, we're not 100% sure, but we think it's too heavy to be the only other kind of object that is this compact and massive, compact enough to produce this signal, a neutron star. And so it is really quite exciting. We've seen something in this unknown region between black holes and neutron stars. We don't know which it is. And unfortunately, it was so small that it was swallowed whole by the black hole. If it had been a neutron star and the big black hole had been smaller, then there could have been a wonderful optical display from the tearing apart of the neutron star by the black hole, but this one was swallowed whole. However, on August 17, 2017, there was a collision of two neutron stars. Each neutron star had a diameter of about 20 kilometers. It was about 1.5 times heavier than the sun, made of pure nuclear matter. The two black holes spiraled around and around each other and emitting gravitational waves as they went. They then collided and created a giant fireball of hot nuclear matter exploding out into the universe and emitting electromagnetic waves as it went. Here is the gravitational waveform, very different than the one that the first one was a very brief waveform. This lasted in the LIGO frequency band for 100 seconds, sweeping up in frequency from 24 hertz, 24 cycles per second, to about 1,000 cycles per second. When it left the LIGO frequency band, the collision was probably at around 2,000 hertz, something like that. 1.7 seconds after the signal, the last bit of signal came in, a burst of gamma rays was seen by the Fermi Gamma Ray Telescope and also by the Integral Gamma Ray Telescope. LIGO, together with a partner gravitational wave detector in Europe called Virgo, which had just turned on within the previous month, it identified the location on the sky. This is a map of the sky. Identified that the source was in this small error box on the sky. And then over the following hours, the astronomers saw X-rays, ultraviolet, optical, infrared, radio waves, all forms of electromagnetic waves that astronomers observe the universe with, coming from a galaxy down right inside this error box. So this was really quite a marvelous discovery. It was the first example of what we call molded messenger astronomy, gravitational waves being used as one kind of messenger, together with electromagnetic waves, another kind of messenger, and all of these different species of electromagnetic waves all together. It was the largest collaboration of astronomers in the history of astronomy. I've been told that something like a quarter or 20% of all the astronomers in the world observed this event with all these different kinds of telescopes. The science that came off of this multi-messenger astronomy event was just fabulous. For example, From the electromagnetic observation, it was inferred that enormous amounts of gold and platinum and other heavy metals were created in that collision of the neutron star. This had been predicted, but had never been seen any evidence for it. It had been predicted the neutron stars would do that. We now think it likely, based on the numbers that come off of this observation, that a large fraction of the gold and platinum in the universe is created in this way. Well, gravitational wave astronomy and multi-messenger astronomy are just at their beginning. We've just seen the first baby steps. LIGO-India is crucial to the future of this gravitational wave astronomy and multi-messenger astronomy. For example, we want to know, in order to go look for electromagnetic sources, we need to know where is the source on the sky. Now, if we have just the LIGO network, because the key thing is that all of the LIGO detectors are run in common with very tight and close collaboration. We just have a LIGO network, then without a LIGO-India, the error box for a source on the sky is these purple error boxes. They're enormous, they're long and thin. We determine where the source is by the delay in the time of arrival at the detectors. And so with just 2 LIGO detectors, the first signal, the signal first arrived at the detector in Livingston, Louisiana. 7 milliseconds later, it arrived at the detector in Hanford, Washington. Washington is roughly north of Louisiana. The fact that it arrived in Louisiana first and Washington second tells us that the signal is coming from the south. And so that's the way that we determine then that the signal is inside this error box or that error box. With LIGO-India, the error boxes are the tiny blue ones. Enormous improvement with India coming on. The area of the error box is reduced by a factor of about 20 on average, down to about 10 square degrees typically. The distance uncertainty is reduced by a factor of 3. LIGO can determine the distance to sources from its observations. That's one of the direct observables with electromagnetic astronomy. Its distance uncertainty is reduced by a factor of 3, so the uncertainty in the region in 3-dimensional volume where the source was is reduced by a factor of about 60 by just bringing LIGO-India on board. Now, if there are other detectors operating, which there may or may not be, a Virgo detector and possibly a Kagra detector in Japan, if there are other detectors, then they will also help, but not nearly as much as LIGO-India helps. The key thing is LIGO-India is considerably farther south than any of the other detectors, and that enables us to reduce the size of these error boxes in the north-south direction by a very large factor. So LIGO-India is absolutely crucial to determining the directions of the sources. And the event rates are also improved by using LIGO-India. Without India, in the early era when LIGO-India is actually operating, now this is now getting up into the middle 2020s, when you may be in middle and toward the end of the 2020s, we may be seeing 500 binary black holes per year without LIGO-India. With India, about 750. So an improvement by about 50%. And binary neutron star collisions, about 33 per year without India, 59 per year with India, according to the simulation. And so that is buying us more than a factor of 2. And so this is really crucial also for getting large event rates for doing very rich science. Let me give you some examples of likely discoveries with the aid of LIGO-India. We expect that it is very likely we will watch neutron star that is orbiting a black hole be torn apart. And that from the electromagnetic observations and the gravitational observations together, we will be exploring the properties of nuclear matter with very high precision and great richness of studies. We will expect, if you have if a final black hole is spinning slowly, the shape of the final black hole's space in higher dimension looks like this. This is the funnel that's representing the final black hole. The color coding is the slowing of time. If the final black hole happens to be spinning very rapidly, the throat in higher dimensions is much longer. And it turns out then that it is quite possible that these final normal modes of oscillation that emit the gravitational waves after the two small holes merge to form the final black hole, that they will interact. They'll be trapped inside this throat long enough to interact with each other in what we call a nonlinear manner and produce the analog of turbulence in the atmosphere, or turbulence in a storm in the atmosphere or at sea. And this wild turbulence in the shape of space and time would be fantastic to verify that it can occur and to study observationally. We expect with LIGO-India to see spinning neutron stars in the form of pulsars, or what is called low mass X-ray binaries. We can study jointly with electromagnetic astronomers and learn a great deal more about quiescent neutron stars in that way. We expect, if we're very lucky, to see one or two cores of supernova explosions, and thereby for the first time get a real handle on what happens inside the core of a supernova explosion. It's quite possible we will see some other things that are much more speculative. Cosmic strings. These are defects in the shape of space with a core that is made of fundamental physics fields. Of the core inside this defect, they're in the form of strings that reach across the universe that can have kinks on them like this that travel down the string, emitting gravitational waves with a very unique waveform, a very unique shape of the waves. LIGO is searching for gravitational waves from these things. These may have been formed in the birth of the universe. We don't know. We don't have no evidence for them, but it would be wonderful if we see them. Stochastic gravitational waves from other processes in the very early universe are a possibility. To actually be observing what went on in the very early universe is a goal of gravitational wave astronomy. LIGO, with the help of LIGO-India, might, if we were lucky to see something like that, probably not, but it is a possibility. And huge surprises are very likely. I'm going to give you one example of a wild example, very speculative, that our universe might have been formed as a if I show it like a two-dimensional surface instead of 3 dimensions, it might look like this, all crumpled up and wrinkled when it was formed. And this is in a higher dimension, we see it. And when adjacent pieces of the universe discover that there are wrinkles in between them, there's great tension, according to theory, in our universe. And that tension will cause it to straighten out very quickly into a smooth surface. And that straightening out process would produce a very strong burst of stochastic gravitational waves from the early universe. Highly speculative, but just I give it to you as an example of the kind of huge surprise that could come. Indeed, I think it is very likely, it's essentially guaranteed, that gravitational waves will bring us a revolution in our understanding of the universe. And that is the most exciting aspect of this. So within 15 years, we will be observing gravitational waves in 4 different frequency bands. These are the analog of gamma rays, X-rays, light, radio waves, but for gravitational waves. There will be the LIGO frequency band in terms of periods. This means in frequencies, this is frequencies of thousands or hundreds of hertz, so periods of milliseconds. There will be detectors in space, such as something called LISA, which will observe gravitational waves of periods of minutes to hours, something called pulsar timing arrays that observe gravitational waves of periods of years to decades, and something called the polarization of the cosmic microwave background, and see patterns on the sky produced of polarization of microwaves produced by gravitational waves for periods of hundreds of millions to billions of years. And so it's not just ground-based astronomy. We're going to have a burgeoning of astronomy in different frequency bands over the coming 20 years. When we look back on the period of the Renaissance in Europe, and we ask what is our legacy that we got from that period, we often say, we in the Western world, great music, great architecture, great art, and the scientific method. And when our descendants, a few hundred years from now, look back on our era, what will they say is their greatest legacy from us? I suspect it will be an understanding of the universe and of the fundamental laws that govern the universe. And LIGO will be a major contributor to that. Thank you.
Thank you. Thank you very much, Kip, for that fascinating snapshot of the science of LIGO, what we've seen and what we are going to see. And I think let me invite Rana now to take us through how we actually get to know this, get to see these signals, and what are all the exciting things we can do with the technology coming out of gravitational wave science. Rana.
Everyone see my slides?
Yes.
Good. Right. So mainly what I want to describe to you today is the technology of how the gravitational wave detectors work, and then also get into a bit what use are these technologies outside of this field. So you've already heard about the basics of gravitational waves, and let me spend a few minutes to walk you through the experiment and the instrument and how does that work. Roughly speaking, it's like this image you see on the left, the gravitational waves from space. And our instrument is a laser interferometer, which makes a differential motion of the strain in two different directions. And as the space-time is warped, it affects the path of the laser beams going through it. And we make a detection of the light beam using this photodiode at the output port. And a bit later, I'll talk to you about this box that says squeeze light. On the right-hand side is just a very old image of what these kinds of machines could look like, that there are partially silvered mirrors and a laser and a box and so on. And today's detectors are much more sophisticated, but the schematic diagram looks very similar. So if you understand this picture, then you should understand the whole thing. At the moment, within the LIGO project, we have the two detectors in the US on opposite sides of the country. And we have plans to build this third detector in India at the Aunda site in Maharashtra, close to the Hingoli district. And there's a CAD drawing on the right-hand side showing what it would look like. And the aim is to have all three detectors identical, in that as we upgrade the LIGO detectors, all three should be upgraded at the same time. And then these will be the world's leading detectors in terms of sensitivity. And I'll show a bit about how that works. So on a map of the world, one of the maps of the world projections anyway, you can see these three yellow LIGO detectors. We'll have one in Europe called Virgo and one in Japan called Kagra. Whereas all the LIGO instruments use the same technology, the Virgo and Kagra detectors use somewhat different technology, and so their sensitivity for different sources will be different. This is a bit of a more detailed view showing where the LIGO-India site will be. It's nicely centrally located from many of these institutes who are already collaborating with us, whether on experiment or theory. And here I've highlighted these large bluish circles, some of the nodal institutes involved in the work. There's the Institute of Plasma Research, the Raja Ramana Center for Advanced Technologies, and the Inter-University Center for Astronomy and Astrophysics. Essential to understanding what these instruments are and how they work is to think about both the signal and the noise when we think about how they how they work and how we can make them better. And so I show you this slide, and I encourage you, if you're interested, go to this website at Cardiff, where all of our signals, all of our confirmed detections up to this point have been displayed in this easy-to-use gravitational viewer. Before I get into the details of the instrument and the noise, I want you to look at sort of what are the similarities and differences of these signals. So if you look all the way at the top, there's our first signal, our beloved GW150914. The signal lasts for a very short amount of time, but the amplitude is very large. And if you look through all of these signals that we've gotten so far, it's sort of remarkable to me that our first signal is still the loudest, the one from 2015. That's interesting. It's short. You can look at some of these other ones. What else is remarkable here? You can see this yellow one, GW170817 that Kip talked about. This was the merger of two neutron stars. And if you look here, not only is the amplitude very small, but the signal lasts for an incredibly long amount of time compared to the binary black hole. And that's roughly to say because the signals which come from stars of small masses, neutron stars or small black holes, their radiation efficiency is low. There's less energy coming out, and so they take a longer time to inspiral, and therefore the waveforms are long. So you can listen to these things as you listen to the audio of the data on your headphones at home, and you can start to understand something about what are the sources, where do they come from, by the musicality of these signals when you listen to them. It's not necessary to use sophisticated signal processing to understand the character. For example, our first signal, 150914, it's a very low frequency signal. And you can imagine, roughly speaking, the lower the frequency, the heavier are the black holes. And the 150914 is makes a very deep sound when you look in the data. It's about the deepest sound that maybe human beings can make. And if you play that through your audio speaker, it will sound a bit like That's the best impression I can make. But roughly speaking, it starts at the low frequency and then chirps up to high frequency before there's a final burst, and that's the ringing that. So that's the signal. That's the thing that we're interested in. Now, this is a cartoon of the instrument, and these will be more or less the fundamental sources of noise that limit also the LIGO-India detector. And I'll say a few things about them, but I won't go into too much detail about how the instrument works. There's a laser which illuminates the whole system, and it is much like a Michelson and Fromger, as I showed you before. There are some of these extra optics in here. And so, for example, if you look in this place where the red bar is highest, that's to indicate that the laser power there is very high. And effectively, the length of the instrument is increased by allowing the light to bounce back and forth between these mirrors for a long time. And roughly, the increase in the length of the instrument is a factor of 100 or 200, based upon the properties of these optics. The main limits to our detection are the quantum mechanics of the electromagnetic field, the laser field that we're using, and also the thermal vibrations, thermodynamic vibrations of the equipment that we're using to make the measurement, in this case, the mirrors. And those two are essentially the main obstructions to us detecting black holes even further out in the universe. Those are fundamental, but there are other ones which are very important. Here I'm showing you now sort of a complicated plot, but let me walk you through it. This is meant to describe the noise of the instruments rather than the signal, but to guide your eye, I've showed you this green bar here, which says 150914, and that's roughly the amplitude of the signal as a function of frequency as the signal came in and merged. And you can see that the integrated power is most at low frequencies, and then the cutoff at a few hundred hertz is after the two black holes have merged. And that's plotted relative to the sensitivity of the various detectors. The LIGO detectors are shown in red and blue. They're a bit different here. The detector Virgo was on at the same time and shown here. And then also the detector in Germany, GO600. And I've drawn here, in addition to these various curves, I've also shown you the limits that come from quantum mechanics in purple, and then from thermodynamics in orange. And besides these limits, you can see that there's a bit of a gap between these fundamental limits and the actual performance of the machines. And that has to do with a host of technical limits, which I'll now describe to you. And before I get into it, I'll just say there is a lot of technology involved here, but it's all a matter of complexity. The essential physics which goes into each of our technologies is not so complicated, and so it's quite simple to understand. Even if you're just getting started, you'll see that many of the things are simple concepts which build and build and build to become complicated. So this is the cartoon I showed you again, with various noise sources highlighted. In addition to the fundamental things, I want to draw your eye to this thing at the top, seismic and gravitational vibrations. Now, the challenge for us is that the Earth is vibrating and everything is loud. And we're trying to measure very small signals in this noisy environment on this planet. And how do we do it? Well, the first thing that we do is we amplify the signal as I described. So we bounce the laser light around within these optical resonators. And eventually we build up to hundreds of kilowatts of laser power in our system. That allows us to really, really amplify the effect of the gravitational wave signal. And there are problems that come from that. One is that the laser light requires a completely empty path in order to make such sensitive measurements. If it traveled through an atmosphere, it would be disturbed by the molecules and pressure. And so we've built these very large vacuum systems so that the entire 4-kilometer path is about 1 billion times more empty than the atmosphere that we have. And this work for LIGO-India is going on at the Institute for Plasma Research, and I've put the link here so you can look at the nice work they've been doing even under lockdown. Another of the key technologies for us is to understand the quantum mechanics of the light field that we're using to probe the system. And that's where the concept of squeezed light comes in. Squeezed light, I think, is a nice example of how theory and experiment can work together over the decades. Some of the concepts to invent squeezed light were started in Kip's group back in the 1970s. And he nicely showed you this large increase in the event rate, how many black holes we detect as a function of time. The key thing in that change from a small number of detections to a large number of detections was the implementation of squeezed light within the LIGO detector. And it's amazing that changing just this tiny bit, what is going on actually with the vacuum state of what is going on with the electromagnetic field of empty space, that this allows you to make such a dramatic improvement in the detection. And to give you an idea of what that is, I've shown you these waveforms on the top left. We're trying to measure the amplitude and the frequency of this sine wave. And normally we have the quantum uncertainty of the electromagnetic field, and it affects the electromagnetic field equally at all times. The concept of squeezing is that we take the noise that we have, we don't get rid of it, but we modify it such that all of the noise happens here at the peaks and the valleys of the sine wave. And in this case, we're just interested in the frequency of the sine wave, and so pushing the noise here into the amplitude of the sine wave has very little effect on the phase of the sine wave or the frequency. And that allows us to make precise measurements of the phase by just playing this quantum trick, by changing the statistics of the field. And that is very dramatic. That allows us to get much more sensitivity than what you would expect from just looking at the conventional detector designs. If it was all quantum mechanics, life would be easy. But unfortunately, there are other things going on. This is a bit of a cartoon, and you may laugh looking at it, but these are some of the serious, some more serious than others, but these are some of the serious problems we have when trying to detect gravitational waves on the ground. In addition to usual things like just the ground moving, we also have to worry about gravity caused by nearby sources, people walking around the buildings, or the effect of clouds or turbulence in the wind. All of these things can make motions of the mirrors at the level of 10 to the minus 18 or 10 to the minus 19 meters. So a small fraction of the diameter of a proton. those things are still important to us. And so we have to learn how to handle all of this. And mostly what we do is we place the experiment in a very isolated system, in a vacuum system. That's not really enough. Our next ambition is to go beyond what you can do by protecting yourself only from the noise, but instead to use modern signal processing techniques. We all have heard a lot about machine learning and the magnificent advances you can make, not just in playing video games, but also in astronomy. This has so far not been used to improve the noise of the LIGO instruments, but we have ambitions to look at all of the thousands of environmental sensors that we have and use that in a supervised learning approach to subtract all of this foreground contamination from our signals. And that would allow us to get actually back to the quantum and thermodynamic limits of our instrument. Okay, I'll just spend a few minutes talking about, in addition to these technologies that we use for gravitational wave detections, what else is the purpose of these technologies? What else are they good for? I think as people know, there's a long history of inventions made in the pursuit of curiosity, purely curiosity-driven research. These inventions have a history of trickling into the general use, I would say. For example, the transistor in the 1950s, the invention of the laser to aid in astronomy, the use of general relativity in calculating offsets in the GPS systems, atomic spectroscopy, stable clocks, detection of contamination, et cetera, et cetera. These have largely been driven into industry through the development of the national laboratories and then through the more recently incubation of startup companies at some of the leading institutes. It's not all from gravitational wave detection, of course. There's a lot of technology that comes from the study of quantum mechanics or atomic physics, and that have led to great advances and an incredible boost in the world's economy. Here I'm just giving you a bit of a shopping list of what commercial applications there are of the gravitational wave technology. And I want to just highlight a few of these. I've talked to you already about AI and signal processing. So yeah, more and more, I would say, not just in the gravitational wave field, but a lot of these big data-driven fields, the use of machine learning to do the signal processing and detection has really become the latest thing. I mean, you cannot really make much headway if you're not an expert in this area. Our use of high quality optics and lasers has led to the advances in inertial guidance, which is what you use to shoot things like airplanes around and have a way to tell where you are. Quantum key distribution is a problem in the future for the quantum internet, how we can make encrypted YouTube live streams, etc. That requires the distribution of keys in a way that you know that the key has not been snooped on. And finally, I think in the coming few decades, there is the possibility of quantum computers and simulators, which require all of the techniques that are used in gravitational detection, such as vibration isolation, shielding, stable lasers, coherent controls. I think in the interest of time, let me wind up here. I'll just give you a fast blow through these slides. High quality optics are a great area of research for us. And it's very important to do so to have better and better control of the quantum state for LIGO systems. It turns out to be also really valuable for, as I said, for inertial guidance, but these days, this is also key in startup companies in the areas of telecom and also quantum computing. Some about vibration isolation and AI. Yeah, let me focus on some things about quantum measurement a bit. So you've seen a bit about the signals we have detected, and I've talked a bit about what are the noise limits of our current systems. And I think the question that comes up, the question that I get often from people who are the youngest is, where is this going, or what does the future hold in this field? And I'm personally very encouraged by developments in the field in the last 10 or 15 years. It seems that not just the pure technology of optics and lasers are getting better, but also our theoretical understanding of how we can limit things that ruin our quantum measurement enhancement techniques. And I would say it like this: when I was in school, I thought, well, quantum mechanics, that's a lot of headache. It seems to cause a lot of problems when you're doing experiments, because it results in you having a lot of imprecision. There's the quantum uncertainty. But these days, I sort of see it more as a good thing than a bad thing. With our knowledge of quantum mechanics and how this affects measurements, I think with quantum engineering, we can now arrange the device and arrange the measurement in such a way that we can go far below the standard limits of quantum mechanics and the standard statistical uncertainty that you expect from having quantum imprecision and laser sensing. And this is great for this field. If it works out, we would be able to make orders of magnitude improvement over the next decades. But the technology that we develop for pushing this makes me very excited about what we can also do with small scale devices for other non-gravitational wave purposes, such as health monitoring, preventative failure analysis, and etc. So I just close off by saying, I guess I repeat what Kip said. We're just at the beginning. We are just making the first baby steps. And so we have now, learned how to handle some of the simple problems. I mean, I would say we have solved most of the 20th century physics problems now in the early part of the 21st century. And we are just now getting ready to tackle the new problems of the 21st century. And for that, my feeling is what we need most of all is some talent. We need some bright new minds with some great ideas for seeing how to make the next orders of magnitude improvement in our sensitivity, just as people did in the 1970s and 1980s. And on the right-hand side, this graphic, it's a bit of a cartoon also, but it shows something like, as a function of distance, as you go deeper and deeper into the universe, what fraction of the black holes are you observing, or what fraction of the neutron stars are you observing? And the green line that says A+, this is sort of the sensitivity of the LIGO-India detector that we expect by the end of this decade, that we would be probing a really large fraction of the binary black hole population and set really important limits on the nature of the earliest black holes. But we will still just be getting into the beginning of the distribution of binary neutron stars. And one of our goals is to do really deep cosmology with gravitational waves. And that will require us going further and further in sensitivity, back to a time when the universe was only 1/10 of its current age. And so there's a lot of room to grow in terms of the new science we can get. And I think there's a lot of room to go in terms of the technology we've developed to get there. And so if you're interested in that, I put a link at the bottom about our summer internship programs. And of course, there are many institutes now in India who are getting involved in this. And so there are opportunities for doing research as an undergraduate or for your PhD or so on and so forth. So I would say that the universe is dark, but the future is bright. Maybe that's a good quote to end on. But thank you for your time.
Thanks very much, Rana, especially for laying out all the opportunities for India to be at the head of this new field. And it is truly a real opportunity, and I hope we will be able to get our act together and bring this about. But I think it's time for questions, and I'll hand it over to Professor Ajit Parameshwaran from ICTS to ask to relay the questions to the speaker.
Thank you, Rajesh. So I will start with some questions from the YouTube channel. There are many. Meanwhile, if anyone from the Zoom meeting has any questions, please raise your hand and I will unmute you after taking some of the questions from the YouTube. So one is probably a question for both of you, Kip and Rana. How better are the future detectors going to be? And what are the additional interesting science that we can do with them? Rana, do you want to start with how better they are going to be?
So there's several areas in which there's a number in terms of how much more sensitive they will be. And then there's the character and quality of the signals, I would say. It's a maybe remarkable coincidence to me. All of the signals that we've detected so far, the frequency of oscillation of these signals is within the human audio band. So these are all sounds that people can make with their voice. Our aim in the future is to go deeper in the sense that we want to detect those signals further out in the universe. But then we would also like to detect the very highest frequency signals, which are the vibrations of neutron stars, and to go below the human audio band. There's things that are much more. But I would say maybe the question is geared toward where we are now on the ground and the human audio band. And there, let's say the limits are only in our imagination. Once we've written down the equations of what you can do, you've now given your permission to work on that problem. And so there's no problem in the laws of physics that says we cannot get 10 times or 50 times better than what we have now. And the thing that's tough to, I think, conceptualize, if we make a factor of 10 improvement in the distance that we can reach, because we are looking in all directions, it's something like 1,000 times more sources. And Kip was talking about having a few per day. You can imagine what would happen. We would have thousands of sources per day, thousands of signals a day. It would be a completely different world. And we would be probing the universe in a way that's more like using the gravitational waves as a backlight to illuminate the universe rather than just look at the individual signals. But those are what I'm talking about is not impossible or crazy. These are all things that can be done with enough imagination and hard work.
Would you like to take this ahead?
Yeah, so I'll just say that in the early period of LIGO-India, we should be seeing a large number of neutron star collisions, neutron stars being torn apart by black holes, huge numbers of black hole collisions. I would hope that we may see at least one core of a supernova, and for the first time really get an understanding of what happens in the cores of supernova explosions. The most exciting science, I think, involves the early universe. If we're really lucky, then with LIGO and LIGO-India, we will begin to see some signals from the early universe, the cosmic strings that I spoke about, and then it becomes much more speculative. When we move into the other frequency bands, the optimal band for bands for seeing things from the birth of the universe are at much lower frequencies. And I think the real excitement there is basically to see the birth of the universe and see the birth of the fundamental forces that control, that give rise to everything. And through those observations, help to really pin down the unification of the fundamental forces, the laws of quantum gravity. So that is sort of a sweep of the future few decades. If we just look in the 2020s, we will be getting to the point where we, as Rana's little cartoon figure showed, where we'll be seeing nearly every black hole merger in the entire universe. For these black holes that are made from the collapse of stars or the hierarchical mergers, so black holes with masses in the tens to hundreds of solar masses. and to really see that whole population and begin to study through it how black holes are born through the population studies, how they're distributed through the universe, and what kinds of galaxies they're in, and so forth. It's a very rich amount of astronomy there, just in understanding black holes and then the neutron star distributions through the universe.
Thank you, Kip and Rana. There are related questions. Are there ways to probe dark matter and dark energy using gravitational waves? What can multi-messenger observations tell about various things?
So, to probe dark energy, this is something where perhaps the best way, where we do not expect to see direct signals from the sources of dark energy. They're thought to be some sort of field that is diffusely spread through the universe. So you won't see that. But if we can measure how the rate of expansion of the universe is a function of time, then that is a way of learning indirectly a large amount about dark energy. And gravitational waves joint with electromagnetic waves have the possibility to really contribute to that. Because electromagnetic waves cannot measure the distance to sources with very good accuracy. But gravitational waves can. It's a direct observable from gravitational wave observations of black hole mergers and neutron star mergers. Whereas the gravitational waves cannot very accurately measure the velocities of sources away from us, so-called the redshift, the cosmological redshift. The electromagnetic can. So combining the two together is fairly likely within the next decade or so become a powerful way, perhaps the best way to pin down then the combination of the distance to a source and the redshift, or the velocity of the source away from us, and thereby to determine how the expansion rate of the universe evolved over time, and that gets us a handle on dark energy. Dark matter, dark matter, presumably whatever it is, if it forms the analogs of stars, if there's some what we call a sector in dark matter that involves strong interactions among the dark matter, and you get condensates of things like stars, then those things can collapse and form black holes. Those dark stars can produce gravitational waves. And so there are various speculations about how we might, through gravitational waves, get some handle on dark matter. They are speculations. Whether they will pan out is not clear, but there is some possibilities.
Rana, would you like to add anything more on the possibility of using gravitational wave detectors as probes of dark matter and so on?
I think, I mean, the only other thing to add is I think there's the possibility, not possibility anymore, but like a reality of using gravitational waves to probe the dark matter density through the effects like the warping of space, lensing, etc. But then we can also, I think it's interesting, also really out there and speculative, but to wonder whether or not something happens within the dark matter that affects the wave in a different wave than what you get through propagation through empty space. And I think it's a thing we didn't talk about yet, but because the Earth is round, the LIGO-India detector will be rotated relative to the detectors in the US. They'll be not really oriented in the same way. And so by combining the data streams from these two things on opposite sides of the globe, we're able to deduce something about the polarization of the waves, whether they're up or this way or that way. And I think that's an interesting test yet to make of the, it's a thing no one has observed, is what is the effect of dark matter on the polarization of gravitational waves. And that I think India will allow us to do for the first time. And I'm curious to find out what happens.
Right. Okay, yeah, thank you. This is probably a right time to switch into some interesting other topics. So there is this question that several people ask. And given there are detectors operating in the US, Europe, and Japan, what is the additional advantage that LIGO-India will bring into the table? And what exactly can it contribute? Is this the kind of right investment to make?
So let me just remark that as I showed this indication of the accuracy with which you can determine the location on the sky, I didn't show actual graphs for it with the presence of Kagra in Japan and Virgo in Europe. But LIGO-India still improves the angular resolution on the sky by a very large factor. We need a detector in the southern that is much farther south. The South Pole would be the ideal place, but we're not going there. And India appears to be the only realistic possibility for something that is much farther south. And so for me, getting modest size, small size air boxes on the sky is tremendously important. And LIGO-India is the only game in town for that. The locations in Japan and in Europe just don't cut it. The other thing is that we know from experience that having the two LIGO detectors, they're under common overall management and they're tightly coordinated in terms of the technology from which they are built, the sensitivities that they wind up at, and tight coordination on observations. That has made a huge difference. And we have seen Virgo in the same time frame not having nearly the same sensitivity, and not being able to operate on the same time frames. So we have some experience that the commonality of the tight coordination between the LIGO detectors really is an enormous factor in terms of in the real universe and pulling things off.
Thank you, Kip. Rana, would you like to add anything more on?
Yeah, I think the question of investment is a good question. Large projects like this are inexpensive, and so I think it's very reasonable for people to ask about, is this the right direction, or is this the right place to put our resources? And I think it's a good debate to always have continuously as we go forward. But I think in the history in other places, what we have seen is that when you have a project like this, people are very excited and passionate about pushing it forward, that the developments that they make in order to make the experiment work have a lot of external payoff. And so if we just think in pure economic dollars, the funds put into basic research, which will be required to make this work, pay off in the long term with a huge dividend through the generation of startup companies, through companies which produce things that feed the experiment and so on. But I think even more valuable than that is the training of human capital, I would say. So one of the reason I have always wanted to do this project in India is because of the vast wealth in terms of talented students who can work on this. And it's difficult to get that kind of large pool of students anyplace else. And the people who will be trained by making this kind of thing work, looking at the data, doing the simulations, it will be an enormous, highly trained workforce. And not all of them will end up spending their lives thinking about black holes like Kip and I do, but instead they'll go off and think about something else just as important, but maybe less mysterious. And I think that is the real gain in this kind of investment. That not only does India become a lead player in this field, astrophysics and cosmology, but over the next couple of decades, the dividends from this will really pay off.
That's a great answer, Kip and Rana. Rana, you particularly alluded to this possibility of gravitational lensing. So you said that one could possibly use the gravitational waves as a backlight to illuminate objects in between. So there are more sort of basic questions on this idea. So does gravitational lensing affect the propagation of gravitational waves? If yes, what are these effects? Is it possible to expect interference and diffraction of gravitational waves, possibly through lensing?
Let me.
Yeah.
Okay, so I'll begin. So it turns out that if you take electromagnetic theory and gravitational theory, the nature of the fields is extremely different. The manner in which they act on matter is very different, stretching and squeezing versus pushing charged particles back and forth. But when you go to very short wavelengths for waves, it turns out the waves have almost the same properties. They propagate along rays, light rays, in the electromagnetic case, call them gravitational rays if you wish in the gravitational case, but they're precisely the same rays. Therefore, they get deflected in precisely the same manner by gravity of other objects like dark matter. And in this short, very short wavelength limit, it turns out that the amplitude propagates in just the same way, in such a way as to conserve photons in the electromagnetic case, to conserve gravitons in the gravitational case. Even though we never see gravitons, the fundamental theory of the propagation is the same. So interference is precisely the same. It's really quite remarkable how aside from the physical effect of stretching and squeezing versus pushing electrons back and forth, it's basically the same phenomenon in terms of wave propagation. And that is quite remarkable to see. For me as a theoretical physicist, this young man, when I first saw this drop out of the mathematics using what's called a short wavelength approximation in physics, I just found it incredible, but it is true.
Thank you, Kip. This is fascinating, certainly. There are other sort of parallels between the electromagnetics and gravitational waves that you sort of alluded to. One is the possibility of gravitational waves coming from the early universe. So a question on that is, just like we have a cosmic microwave background, can we have a cosmic gravitational wave background? If so, what can it tell?
You want to take that, Rana, or shall
I? Go ahead.
So, the key difference between gravitational and electromagnetic waves is that the gravitational waves are much more penetrating. So they produce any gravitational waves that might have been produced in the very early universe will travel through the dark, through the very dense matter of the early universe unscathed, not being scattered at all, not being absorbed and re-emitted. Whereas electromagnetic waves produced in the early universe, they just can't reach us. They get absorbed and then re-emitted. They lose most of their information. They get scattered, lose some of their information. So gravitational waves are our only kind of wave, our only tool for probing the earliest moments of the universe. How do they get produced? They don't get produced thermally like the electromagnetic waves do, because they're not interacting with the other matter to get thermalized. So anything that may come off of the very early universe will not be a thermal distribution of energy. In fact, that means it will be carrying us direct information about what's happening in the very early universe. It does not get thermalized, and so it does not lose its information in that way. Theory says that, let me start over here. The most conservative statement about what came off of the very early universe is that nothing except vacuum fluctuations, the minimum fluctuations of gravitational waves that nature will allow, that's what came from the Big Bang. And if that is correct, and that's what most of the theorists think it probably was just minimum quantum mechanical fluctuations, we are almost certain on the basis of various observations that there is a period of very rapid expansion of the universe near the beginning that is called inflation. And inflation, we know with high confidence, will have amplified those vacuum fluctuations to produce a rich spectrum of gravitational waves that are strong enough, very likely to be detected not by LIGO, but by these by very advanced detectors that operating at frequencies or wave periods around a second to tens of seconds, which is in between LIGO and so-called LISA band, the band of something has been proposed called Big Bang Observer. And so those could be seen in that frequency band after having been amplified, and they could be seen at very long wavelengths by so-called polarization causing microwave background, but that conventional prediction that nothing but quantum mechanical fluctuations came off the Big Bang, those amplified waves would not be strong enough in the LIGO band for LIGO to see them. However, what actually we do see will be a convolution, a combined influence of what came off the Big Bang, which might not have just been fluctuation, and the influence of inflation. And there are speculations that about what might have come off the Big Bang that when combined with inflation would produce strong enough waves to be seen in the LIGO. And so we don't know whether LIGO will see them or not. I'm almost sure that these other technologies will see them by about the middle of the century. And one of them might even be seen within the next few years with the CMB polarization. But the exciting thing is that you have sort of a minimal prediction that it should be observable, and you have the fact that those observations will tell us about some combination of the very birth of the universe, what came off the Big Bang, and this so-called inflationary process.
Thank you, Kip. Very exciting indeed. Perhaps the second last question is on related to the technology. Rana, you sort of alluded to this active noise cancellation technologies that could be the future of many things. So, so the question is, can earthquakes affect the readings of LIGO, and what can we do to minimize it?
Yeah, indeed. Earthquakes today are a sort of a larger problem, but it's a very solvable problem, I would say. And this has to do with this big discrepancy in the seeming discrepancy in the numbers. We're detecting these very minute fluctuations that are smaller than the size of a nucleon, smaller than proton or something. But we're doing that in the audio band. So it's not that we're making a absolute measurement like this, but we're measuring a fluctuation, which is that small. And when the earthquake happens, the largest amplitude earthquake waves have a period of sort of 30 seconds or something like that. And anytime that there's an earthquake more than roughly 6.0, 6.5, the whole world is shaking like this. And when we have these really huge ones like 9.0 or some 9.2, some of these ones, the earth rings like a bell for long time. I mean, hours and hours and hours. It just keeps going like this. And so when those very large ones happen, the LIGO instruments are sort of overwhelmed. And that's because of the amount of the shaking is quite large. It's some fraction of a millimeter, which is really, really tiny for us, but very dramatic for atomic scale instruments. However, this is all kind of predictable. Earthquakes are not a quantum mechanics phenomenon. So it is possible to measure the earthquake at the source and have a model for the Earth and predict exactly how much the vibration will be on the other side of the Earth. And you can send that information, nearly at the speed of light. And so the LIGO detectors, if they know what is the model of the Earth, where the earthquake originated, that signal can be subtracted off of the LIGO detectors before the earthquake arrives, and essentially keep the detector still, because you know exactly what is about to happen. So you can do a predictive earthquake cancellation. This is not the same as predicting earthquakes. It's knowing that there is an earthquake and then predicting the effect maybe 5 minutes in the future. And with that, that is a technique we are thinking about. And essentially what we do for that is we have our own seismic monitors. And so we detect earthquakes over the world. And then eventually we train our machine learning networks to predict the correct waveform. And that is still ongoing.
Thank you, Rana. Perhaps since we are completed 90 minutes, we could sort of end with a more sort of broader philosophical question, which either of you are willing to take. How will the study of black holes will change our perception of space and time? If this seems to be your favorite topic.
Well, black holes are made from warped space and warped time. And if you look in detail about the nature of that warping, you discover for a spinning black hole sticking out of the north pole of the black hole, there is a vortex of twisting space. So that if I'm there above the black hole, I have a gyroscope, an inertial guidance gyroscope at my feet and one at my head. My head will see my feet, the gyroscope of my feet precessing around counterclockwise. My feet will see the gyroscope of my head precessing around counterclockwise. It's like taking a wet towel and you're trying to wring the water out of the towel. Your right hand sees your left hand going counterclockwise. Your left hand sees your right hand going counterclockwise. There are these counterclockwise vortices of twisting space at the north pole and south of the pole of the black hole. We didn't even know about these until recently. We learned about them from computer simulations to try to understand sources of gravitational waves, and then doing the theory afterwards. There are tendencies that stretch and squeeze that stick out of the black hole itself as well. So we've learned that there are structures made from warped space and time attached to black holes. And we have predictions of what are the gravitational wave shapes that are produced when the black holes collide and those structures interact, and how structures behave. The shapes of the gravitational waves are determined basically by the behavior of these structures that stick out of the black holes, mostly the tendencies, to some extent the vortices. And gravitational wave observations are verifying the predicted shapes of the waves, and are therefore verifying these aspects of the warped space, these structures of warped space and time that stick out of black holes. So we really understand the details of warped space-time quite differently than we did 20 or 30 years ago, and gravitational wave observations are verifying.
I'm glad Kip answered that question first. I interpreted the question in a different way. I think I've been working on this a bit less than Kip, only 20 years. But when I think, how does it change my understanding of space and time? It's I've understood that difficult experiments take a long time. So time, when you say, oh, it took a couple of decades or 5 decades or something, now I feel like that's not such a long time. If you want to do something great, maybe that's just something you need. And then I think my knowledge of space has also changed, in that in order to make these things work, it's been an incredible cultural experience for me. I worked with so many scientists from different countries all over the place and traveled around to meet with them and work on these various detectors over the world. So time has become contracted, I guess, and space has become contracted. Usually you don't get both at the same time, but that's working in this kind of scientific experiments has made me feel like the Earth is small and time is moving very rapidly. And so a few decades passed just like that. You know, just yesterday I was turning on my first laser, and now here we are.
Thank you very much, Kip and Rana, for bringing together this theory experiment and the culture of this real exciting frontier of science. Thanks a lot for getting up very early in the morning. Rajesh, would you like to make any final remarks?
No, I just wanted to thank both of you, like you said, for being up so early and addressing all of us. And I think especially on YouTube, there's been a huge number of people following the lecture. And so I'm sure it was very inspirational. So thank you.